Good morning, everyone. We are from Computational Thinking Class 04, Group 9, and today we will present our solution for case study number 9, which will be smart parking system in urban areas. This project applies computational thinking principles to solve the real-world problem of urban parking inefficiency. So our team consists of 5 members with clearly divided responsibilities. So I handle the problem description, pattern recognition, and data representation. Mohammed Jimboy focuses on the algorithm flowchart, and Mohammed Elgi develops the pseudocode, while Nafal Faiq conducted the big O analysis. This division ensured comprehensive coverage of all computational thinking pillars. So, problem description. The urban parking problem has 3 core objectives: developing a real-time guidance system, reducing traffic congestion, and efficiently balancing competing factors. Our system processes inputs including available spots, driver destination, parking fees, and traffic congestion to output a single recommended spot. The main challenge lies in the conflicting requirements where improving one factor often worsens others. So, for example, the closest spot may be expensive while the cheapest spot might be in a highly congested area. So here is the table. This table clearly illustrates the trade-offs we must consider. The closest spot offers minimal walking distance, but comes with high cost and possible congestion. The cheapest spot saves money, but is often far and inconvenient. Meanwhile, low congestion spots provide easy access but are typically distant locations. These conflicts confirm we need a multi-criteria optimization approach rather than a simple sorting algorithm. Right. Moving on to pattern recognition, we identify 3 key computational patterns in this problem. First, the iterative processing for systematically evaluating all available spots. Second, conditional filtering based on user constraints. And third, a scoring mechanism for quantitative comparison. The core pattern is a multi-criteria optimization similar to how civil engineers balance material cost against structural strength. We must balance distance, cost, and congestion, where improving one factor often worsens others. This pattern recognition directly led us to choose a weighted scoring model. So we move on to data representation and abstraction. Here we see the complete data processing pipeline using real San Francisco parking data. We start with raw metrics like 250 meters distance, $8 fee, and 45 vehicles per minute congestion. These are normalized to a 0 to 1 scale, then weighted according to user preferences. The scoring calculation shows how each factor contributes to the final score. And based on this analysis, 50 Vermont St. Garage merges as the optimal recommendation with a highest score of 0.52. And we offer the best balance of short distance despite the higher cost for our sensitive user scenario.
Hello everyone, my name is Mohammed Jamir Fazim and I'm going to explain the flowchart that we have. So basically, our flowchart starts with input and basically applies the available spots and driver destination and the user distance and fee towards the parking spot. And then it initializes, which are 2 key variables that we have in our flowchart that set the maximum score to a very low value to ensure the first real score will replace it. And we set the best spot to null, indicating no selection hasn't been made yet, and this prepares the system for the main evaluation phase. And for each spot available in spots that we have an input, it calculates the distance. And the calculate the distance for the spots and the location of the spot and the driver distance. And then we have a normalization of distance, max distance, and phi and congestions to a common 0 to 1 scale. This normalization allows us to compare these different measurements units fairly. After that, we calculate a composite suitability score by applying the user's weight preference to normalized value. Then the system makes a decision if the current score is the best or if it's a max score. If not, then we continue with the next spot. If yes, then that's it for the loop of the whole thing of finding a parking spot. After that, it outputs as the best spot, and then the user or the driver finds a spot. Thank you very much.
Hello everyone, my name is Muhammad Agiran Putra and I'll be present the pseudocode for our smart parking recommendation system. This system helps drivers find the best available parking spot using real-time data, preferences, and scoring logic. Okay, so in the first stage, we define the main data structures. We have a list called parking spots where each object contains ID, location, and availability status, parking fee, congestion level, and last update time. We also define the driver object, which includes the driver's destination and preferences such as maximum fee, maximum distance, and congestion preference. Then we assign weights or for distance, fee, and congestion that will be used in the scoring calculation. Next, we create several utility functions to support the main process. First, fetch real-time data, retrieves live updates from sensors or APs. Second, calculate distance, computes the distance between the driver's destination and each parking spot. And third, normalize, standardize all numeric values between 0 and 1 to make them comparable. So these functions ensure that our system always works with the latest and consistent data. Next, compute scores. In this stage, the function compute scores calculates a performance score for every parking spot. We first collect distance, fee, and congestion values, then normalize them. Each normalized attribute is multiplied by its weight, distance 0.5, fee 0.3, and congestion 0.2. The smaller the final score, the better the parking spot. We also store the computed distance for later sorting. Next, uh, filter by preference. After calculating scores, we use filter by preferences to remove unsuitable parking spots. This function checks if the spot is available, if it is within the maximum fee and distance limits, and if congestion is acceptable based on the driver's preference. Only the filtered result continue to the next process. Next, sort spots. In this step, sort spots orders all candidate parking spots. If the drivers wants to sort by distance or fee, we use that preference. Otherwise, we sort by the total score where a smaller score indicates a better recommendation. When there are ties, the system breaks them using fee, distance, and congestion as secondary criteria. Next, uh, reservation process. After sorting, the system takes the top recommendation, the attempts to reserve it automatically using reserve spot. If the reservation fails because another driver took it, the system will attempt to the uh, reserve one of the top three alternative spots. Next, suggestion alternatives. If all reservation attempts fail, suggest alternatives provides the top three alternative parking spots. If no spots are available, the system suggests parking at the nearest hub or using public transportation options. Next, main flow. The main program starts by fetching real-time parking data and receiving the driver's input. Next, it filters and scores the available parking spots, then sports them. The system displays the best recommendations along with alternatives if the driver chooses the reserve. It performs the reservation process. Finally, it continuously monitors updates until the driver arrives at the parking spot. And then the last one, uh, the dynamic monitoring. In the last stage, while the driver is on the way, the system keeps checking real-time updates every few seconds. If the recommended parking spot becomes unavailable, it automatically recalculates and updates the recommendation. Once the driver arrives, the system ends the process. And that's it. So this pseudocode demonstrates how a smart parking system can make real-time, data-driven recommendations, improving efficiency, reducing congestion, and saving time for drivers. Thank you.
Hello everyone, my name is Noval Faiz Anwar and I'm from Civil Engineering International Program and my student number is 24064486663. So today I'm gonna explain about algorithm analysis or Big Zero. So in our smart parking system, the input consists of three main things. The first one is a list of parking spots, including their location, price, and whether they are available or not. So the driver's destination location, and then the last one is it's optionally traffic congestion data. So now for the steps, algorithm steps. First, we collect all parking data from sensors. Let's say we have n parking spots, then and then we filter the available or empty spots. This takes O n time. For each available spot, we calculate the distance to the driver's destination, which is O1 per spot. And we also add other factors like parking fee and traffic congestion. And then next, we sort all the spots based on their total score. For example, by combining distance, cost, and congestion. This sorting process takes O and log n time. And then finally, we select the best parking spot with the lowest score, which takes O1. And then the output is the best parking location in real time. So next is for the complexity analysis. Here's the breakdown of the time complexity, and including filtering empty parking spots, calculating score for each, sorting based on score, choosing the best one. And if we sum all up, it will be ON plus OM plus ON log n plus O1 equals to ON log n. And then for the conclusion, the smart parking system algorithm has time complexity O n log n, space complexity O n, and it is efficient for a moderate to large number of parking spots. And it can be optimized further using a hub or a priority queue, which can reduce the selection time to O n without full sorting. And uh, this is for our case study, and thank you.